Now, to consolidate your understanding of the magnetic dipole moment, I discussed two interesting problems with you in this video. First problem is like this. Think of this as a circular coil. Now, this is a circular coil, and suppose there is a current passing like this. So, in the coil, the current is passing like this. I fold this coil like this. So it becomes two semicircular rings now. It becomes two semicircular rings. This was of radius r, and each is now half ring of radius r. Now just imagine, how will the current flow? I can just imagine like this, and then like this, it will go like this. That's how the current is going. I place this system of two half rings something like this. If I place it something like this, then this part I call it part 1, and this part I call it part 2. So this is part 1 and this is part 2. The part 1 lies in the YZ plane, and the part 2 lies in the XZ plane. The area of each, I can say now, this current carrying coil, so both are two magnetic dipoles. For the first dipole, look at that, the magnetic field is here, that is minus I cap. And for the second, look at that, the current is clockwise like this, so downward, minus j cap, because what is my coordinate system? This is x, this is y, and towards you, this is z. Indian Airlines. So magnetic dipole moment for one, I pi r square by 2, vector wise minus I cap plus I pi r square by 2 area, direction minus j cap. So easy. Once you picturize, look, the beautiful problem, it has now become so easy. So this is equal to minus pi r square by 2 I cap minus pi r square by 2 I j cap. So what is the magnitude of the magnetic moment of these two? Sum total of that, the vector sum, magnitude, this will be root 2 times the magnetic moment of one of them, that is pi r square by 2 into I. So m is root 2 times pi r square. So if I want to break this root 2, so root 2 will come here, the answer would be pi r square by root 2 into I, pi r square by root 2 into I. Direction, well, there was one vector like this for the first dipole, and for the second dipole like this. So m arrow, I can say, lies in the minus x minus y plane, and both the compos are equal, so magnetic moment will be exactly like this, making 45 degrees. So m arrow will be making 45 degrees like this with the minus x axis. Beautiful picturization, and by the use of vectors, so easily you have understood this problem. Let me now take you to a second problem. The second problem is something like this. Now you think of the mithai jalebi. It's something like this. The halwai does this. Look at that. Now of course he does this, but I am doing like this. So there is a current. Just follow my hand. The current is flowing like this. Spiral in the xy plane, spiraling in the xy plane. Total number of turns is n. The inner radius is r1. And then it goes on increasing. All these are insulated turns, they don't touch each other, and the current in each turn is I. Okay, so you follow the system, right? total number of turns are n. So turns per unit length, turns per unit length will be n upon R2 minus R1. This will be turns per unit length, and if I take thickness x. Now what I am doing is, look at this blue shade. I am taking the inner radius x and the outer radius x plus dx. So within this dx, the number of turns are dn. So dn will be number of turns divided by R2 minus R1, where the total number of turns are over a distance R2 minus R1 multiplied by dx. Right. I find the elemental dipole moment dm of this blue area, that will be pi x square area multiplied by I multiplied by dn, that is the number of turns within this blue shaded thing, that is between x and x plus dx. So dn, I just replace. So this will be pi x square I n dx upon R2 minus R1. Then the total magnetic moment, integral of this, constants I take out, pi n I upon R2 minus R1, x square dx, simple integral, x square dx, x cube by 3, limits of integration R1 to R2. Finish, the job is done. So that dipole moment of this system is pi n I upon 3, I take 3 out, R2 minus R1 into R2 cube minus R1 cube. Of course, the direction of M arrow, if the current was going like this, look at that, you are seeing it as clockwise. So here, inside the board, that is minus k cap. So M, the direction of M arrow magnitude is this, and the direction is along minus k cap, along minus z. I hope you have enjoyed my video and understood your concept of.
If you love the video and want me to make more useful videos for you, subscribe my channel and hit the bell icon to stay updated.